Hi everyone, welcome back to video lecture series on RA6M5 microcontroller. In this video, I will demonstrate how to use Octal SPI on EK RA6M5 board. OSPI is extension of standard SPI protocol that allow 8 data line to use in parallel for communication between microcontroller and flash chip. You can study this example project on RA6M GitHub page for in-depth knowledge related to OSPI. This example project shows how to use different mode available for OSPI. Open EK Studio, then create a new project by clicking on the file icon, then select New, then select RA6M C++ project, then select RA6M RA project. A new dialog box will appear. You can give a name to your project here. After naming your project, click on the Next button. From this drop-down menu, select the EK RA6M5 board. After board selection, click on Next. After that, select Flat, Non-Trust Zone project. For Smart Bundles, select the None option, then click on Next. Now select Executable and No RTOS option. Now select Bare Metal Minimal, then click on the Finish button. Now the IDE will take some time to configure your project. Now click on the Open Perspective button to open the FSP configuration file. In FSP configuration file, click on Stack tab, then click on New Stack, then under Storage select OSPI Flash Stack. OSPI stack is giving us error related to clock source. Now click on Clocks tab. In Clocks tab, scroll down to find clock source for OSPI. Here you can change setting related to OSPI source clock. Error related to OSPI clock source is resolved. Now again, open Stack tab, then click on OSPI stack to open its properties. In Properties window, expand General option. Here you can select OSPI channel and mode. We can select from 3 different SPI modes. SPI mode, OSPI with single or dual data rate. In Properties window, you can observe other setting related to OSPI stack. Commands and address are pre-defined here. You can expand Command Definitions option to study different commands related to this stack. Further down in Properties window, you can also check the pins used for this stack. We can also enable support for Direct Memory Access Controller. We don't need to change anything further in the FSP configuration file. Now click on Generate Project Content. After that, click on the Proceed button. Next, expand the src folder and open the Hall entry.c file. Now I will add some source code files to the project, which I copied from the example project on GitHub. These files are OSPI ep.h file, OSPI commands.h, and the .c file. First, include the source code files in the Hall entry.c file. Then I'm defining some data that we will write to the flash device. After that, I'm defining the SPI and OSPI region addresses. Finally, I'm defining the SPI flash direct transfer structure variable that we will use for sending the commands and addresses to the flash device. After that, I'm defining a function that can reset the OSPI memory device when it is called. In the Hall entry function, we can start by defining the FSP error variable. After that, I will call the reset memory device function. Now, in the Project Explorer tab, expand Developer Assistance, then expand the OSPI stack. Next, drag and drop the OSPI open function call into the Hall entry.c file. After that, use the assert function to make sure the OSPI open function call was successful. From Developer Assistance, drag and drop the OSPI direct transfer function call into the Hall entry.c file. First, we will use SPI mode to erase and then write on sector 1. Before sending any command or addresses, we need to use the write enable command. We can use the OSPI direct transfer structure variable for this. And for last argument, we can use SPI flash direct transfer direction write. After that, use assert function to make sure direct transfer function call was successful. To erase sector 1 using SPI mode, we can use the direct transfer structural variable. Here we can define the sector 1 address. Now, from the Developer Assistance tab, drag and drop the direct transfer function call into the hall-entry.c file. Then for the second argument, we can use the direct transfer structure to send the erase command. And for last argument, we can use SPI flash direct transfer direction write. After that, use assert function to make sure direct transfer function call was successful. After the erase command, we can use the RBSP software delay function to wait for the erase command to execute. To write on the OSPI memory device, we can use the OSPI write function call from Developer Assistance. For the second argument, we can use the write data SPI array, typecasted as uint8. For the third argument, we need to provide the sector 1 address, and for the last argument, we can use the size of the write data SPI array. After the write command, we can use the assert function to make sure the write command executed successfully, and then wait for 500 milliseconds using the RBSP software delay function. To enable OPI mode, first we need to send some commands to the memory device. For details related to commands and addresses, you can refer to the user hardware manual for the EK RA6M5 board. Open section 36 for Octa Serial Peripheral Interface OSPI. This section explains the complete register setup, command sequence, and timing requirements needed to configure the OSPI interface properly. Also check the datasheet for the memory device for further assistance. Go through the memory device datasheet. It contains all the necessary information about command codes, voltage levels, timing requirements, and mode transition procedures. First, we will write to configuration register 2 and enable the DQS bit, as described in section 36.8.3. By using the direct transfer function call, first we will send the write enable command. After that, we will define the address for configuration register 2 and the command to enable the DQS bit. Then, again using the OSPI direct transfer function call, we can write to configuration register 2. For direct transfer struct variable, use OSPI command write CR2 SPI mode option. After adding some delay, again we need to send write enable command using OSPI direct transfer function call. To enable OPI mode, we need to write on configuration register 2 and set dummy cycles to 10 for OPI mode according to table 9.3.1 on memory device datasheet. We can use this address and command to set dummy cycles. Now again, we can use this direct transfer function call to send this command. We can copy these 3 instructions from here and paste them here to send the command for setting the dummy cycles. After that, we need to write to configuration register 2 to enable SOPI mode. First, we can send the write enable command using the direct transfer function call. After this, I will define the address and command needed to enable SOPI mode. Then again, we can copy these 3 instructions from here and paste them here to send the command to enable SOPI mode in the memory device. Now we need to update the SPI mode in the EK RA6M5 board. For this purpose, we can drag and drop the SPI protocol set function call from the Developer Assistance tab into the hall-entry.c file. For the second argument, we can use the SPI flash protocol SOPI. Now, to perform the erase and write operations in SOPI mode, first we need to send the write enable command for SOPI. For this, we can use the direct transfer function call. In the structural variable, we now need to set the write enable command specifically for SOPI mode. Now, to perform the erase operation in SOPI mode, first we need to set the address in the structural variable. After that, using the direct transfer function call, we can send the erase command for sector 2. Now, to perform the write operation in SOPI mode, drag and drop the OSPI write function call from the Developer Assistance tab. In the second argument, we can use the write data SOPI array typecasted as uint8. For the third argument, we can use the SOPI reference address, and by the last argument, we will use the size of the write data SOPI array. After that, we can use the assert function and add some delay. Finally, I will hang the processor in an empty while one loop here. The coding part is complete. We don't need to change anything further. Click on your project name, then click on the hammer icon to build your project. After the build is successful, right-click on the project name, select Debuggers, and then choose Renesas GDB Hardware Debugging. Click on the Switch button to open the debug perspective. Now open the memory browser window so that we can verify the successful write operation on Sector 1 and Sector 2. You can find the memory browser window by clicking on Window, then selecting Show View, and then choosing Memory Browser. Start in Memory Browser window, add address for Sector 1 to examine the content that are saved here. After that, I will add a breakpoint after both write operation function calls. Now open Memory Browser window, then click on Resume button. Execution will stop at the Hall entry function. Again, click on the Resume button, and the execution will stop after the first write operation call. In Memory Browser window, we can verify that write function call in SPI mode was successful. After that, again click on Resume button. Now open Memory Browser window and enter address for Sector 2. Here we can also verify that write operation was also successful in OPI mode.